Question 1. Which approach would be most prudent for a network engineer to adopt when implementing OSPF configuration changes across a large enterprise network to ensure optimal routing performance and network stability? Option A. Implement OSPF configuration changes across all network devices simultaneously to achieve immediate network-wide effect. Option B. Conduct a pilot deployment of OSPF configuration changes on a small subset of network devices, followed by a phased rollout based on successful validation. Option C. Focus exclusively on the theoretical understanding of OSPF operation without considering the practical implications of configuration deployment on a live network. Option D. Configure OSPF with default timer values across the entire network without prior analysis of specific network topology or traffic patterns. Correct answer is A. Implement OSPF configuration changes across all network devices simultaneously to achieve immediate network-wide effect. Explanation. Scenario analysis. This scenario presents a professional challenge in network design where a critical routing protocol, OSPF, is being implemented. The challenge lies in balancing the need for efficient routing convergence with the potential impact on network stability and resource utilization, especially in a large-scale enterprise environment. Network engineers must consider not only the technical merits of different configurations, but also the operational implications and the adherence to established best practices and potential regulatory guidelines related to network performance and reliability, even if not explicitly stated as a direct regulation. In the context of a vendor exam, the decision impacts service availability and the ability of the network to support business operations. Correct approach analysis. The correct approach involves a phased and controlled rollout of OSPF configuration changes, starting with a pilot group of network devices. This method represents best professional practice because it allows for thorough testing and validation in a controlled environment before impacting the entire production network. It minimizes the risk of widespread service disruption. By observing the behavior of OSPF in a limited scope, engineers can identify and rectify any unforeseen issues, such as suboptimal timer settings or unexpected routing loops, without affecting all users. This iterative approach aligns with principles of risk management and operational excellence, ensuring that network changes are implemented with a high degree of confidence in their stability and performance. While the 4A0-101 exam focuses on Alcatel Lucent interior routing protocols, the underlying principles of robust network deployment and change management are universally applicable and implicitly expected in professional practice. Incorrect approaches analysis. Implementing OSPF configuration changes across the entire production network simultaneously without prior testing is an incorrect approach. This carries an unacceptably high risk of widespread network instability or complete outage, directly violating the professional responsibility to maintain service availability. It demonstrates a failure in risk assessment and change management, potentially leading to significant business disruption and reputational damage. Configuring OSPF with default timer values across all network segments without any analysis of the specific network topology or traffic patterns is also an incorrect approach. While defaults can be a starting point, they are not always optimal for every network. This can lead to either slow convergence, impacting application performance, or excessively fast convergence, potentially causing instability or unnecessary CPU load on routers. It shows a lack of proactive network optimization and a failure to tailor configurations to the specific environment, which is a hallmark of professional network engineering. Focusing solely on the theoretical aspects of OSPF operation and neglecting the practical implications of configuration deployment on a live network is another incorrect approach. While theoretical understanding is crucial, its application must be grounded in operational realities. This approach ignores the critical need for testing, monitoring, and validation, which are essential for ensuring the successful and stable operation of any routing protocol in a production environment. Professional reasoning. Professionals should adopt a systematic and risk-aware approach to network changes. This involves understanding the protocol's behavior, designing a configuration that aligns with network requirements, and then implementing it in a controlled manner. A key decision-making process involves 1. Thoroughly understanding the protocol's features and potential impact. 2. Designing the configuration with specific network characteristics in mind. 3. Developing a detailed implementation plan that includes rollback procedures. 4. conducting pilot testing and validation. 5. Phased deployment with continuous monitoring. 6. Post-implementation review. This structured approach ensures that technical objectives are met while minimizing operational risks and adhering to professional standards of network reliability and service delivery. Question 2. The review process indicates a need to assess the effectiveness of different high-availability mechanisms for ensuring rapid service restoration following a link failure in an ISIS-routed network. Which of the following approaches best demonstrates a professional understanding of the practical implications of these mechanisms on network stability and convergence? Option A. Analyzing the theoretical configuration steps for enabling ISIS-fast reroute and evaluating its expected impact on routing table convergence time under various link failure scenarios. Option B. Configuring ISIS-fast reroute with default parameters and relying on manual intervention to resolve any routing issues that arise post-failure. Option C. Focusing solely on the cost reduction benefits of a particular high-availability feature, without a detailed analysis of its convergence performance. Option D. Implementing ISIS-fast reroute based on vendor documentation alone, assuming it will automatically provide optimal high availability without further testing. The correct answer is A. Analyzing the theoretical configuration steps for enabling ISIS-fast reroute and evaluating its expected impact on routing table convergence time under various link failure scenarios. Explanation. The review process indicates a need to evaluate the effectiveness of different high-availability mechanisms in a network environment. This scenario is professionally challenging because the choice of high-availability mechanism directly impacts network uptime, service continuity, and ultimately, customer satisfaction and business operations. Misjudging the suitability of a particular mechanism can lead to prolonged outages, significant financial losses, and reputational damage. Careful judgment is required to select a solution that balances performance, cost, complexity, and the specific requirements of the network and its services. The correct approach represents best professional practice because it prioritizes a thorough understanding of the underlying protocols and their behavior under failure conditions. By analyzing the convergence times and the impact of different failure scenarios on routing stability, network engineers can make informed decisions that minimize service disruption. This aligns with the general principles of network design and operation, which emphasize reliability and resilience, specifically within the context of Alcatel Lucent interior routing protocols. Understanding how protocols like ISIS or OSPF react to link failures, router failures, or topology changes is paramount for ensuring rapid and seamless failover. This proactive analysis ensures that the chosen high-availability solution meets or exceeds the defined service level agreements, SLAs, and regulatory requirements for network availability, which are often implicitly or explicitly tied to the operational framework governing telecommunications services. An incorrect approach that focuses solely on the theoretical configuration of a high-availability feature without considering its practical implications during network events is professionally unacceptable. This failure stems from a lack of deep understanding of the protocol's dynamic behavior and its interaction with the network's physical and logical topology. Such an approach risks implementing a solution that appears functional in a lab environment, but fails to deliver the required resilience in a real-world failure scenario, leading to extended downtime. This directly contravenes the professional obligation to ensure network stability and service availability, which are foundational to maintaining trust and compliance within the telecommunications sector. Another incorrect approach that prioritizes cost savings over proven reliability is also professionally unsound. While budget considerations are important, compromising on the effectiveness of high-availability mechanisms can lead to far greater costs in the long run due to service disruptions, lost revenue, and the expense of emergency repairs. This approach neglects the fundamental responsibility of network professionals to safeguard the integrity and availability of the network infrastructure. The professional reasoning process for similar situations should involve a systematic evaluation of available high-availability mechanisms against the specific network requirements, including expected traffic loads, criticality of services, and acceptable downtime. This includes 1. Understanding the protocol's behavior. Deeply analyze how the chosen interior routing protocol e.g. ISIS OSPF handles various failure scenarios including link failures, node failures, and routing loops. 2. Evaluating convergence times. Quantify or estimate the time it takes for the routing protocol to reconverge after a failure for different high-availability mechanisms. 3. Assessing impact on services. Determine how the convergence time and failover process will affect ongoing network services and user experience. 4. Considering redundancy and diversity. Ensure that the chosen high-availability solution incorporates appropriate levels of redundancy and path diversity. 5. Testing and validation. Rigorously test the implemented high-availability solution under simulated failure conditions to validate its effectiveness before deploying it in a production environment. 6. Documentation and monitoring. Maintain comprehensive documentation of the high-availability configuration and implement robust monitoring to detect and alert on potential issues. Question 3. The analysis reveals that a critical OSPF link state database synchronization issue is suspected, leading to suboptimal traffic forwarding on a segment of the network. Network engineers are tasked with identifying the root cause and restoring normal OSPF operation. Which of the following diagnostic steps is the most appropriate initial action to take? Option A. Immediately reset all OSPF interfaces on the affected routers. Option B. Adjust OSPF timer values to accelerate convergence. Option C. Examine the OSPF neighbor adjacencies and the link state advertisement (LSA) database for inconsistencies. Option D. Focus solely on verifying physical layer connectivity and interface status. Correct answer is C. Examine the OSPF neighbor adjacencies and the link state advertisement (LSA) database for inconsistencies. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol, OSPF in this case, experiences unexpected behavior leading to suboptimal traffic flow and potential service disruption. The professional challenge lies in accurately diagnosing the root cause within a complex, multi-vendor environment and implementing a solution that restores optimal routing without introducing further instability or violating established network policies. The pressure to restore service quickly must be balanced against the need for a thorough and correct resolution. Correct approach analysis. The correct approach involves a systematic investigation of the OSPF neighbor adjacencies and LSA, link state advertisement, database, verifying the OSPF state on the affected interfaces, and examining the LSA database for inconsistencies or unexpected entries directly addresses the symptoms of OSPF misconfiguration or instability. This methodical approach aligns with best practices for network troubleshooting, which emphasize isolating the problem to a specific protocol or component. In the context of Alcatel Lucent interior routing protocols, understanding the nuances of OSPF neighbor states, e.g., down, init, two-way, start, exchange, loading, full, and the LSA types is crucial for effective diagnosis. This approach prioritizes understanding the protocol's operational state before making configuration changes, thereby minimizing the risk of unintended consequences. Incorrect approaches analysis. One incorrect approach involves immediately resetting all OSPF interfaces. This is a brute force method that can temporarily resolve adjacency issues, but fails to identify the underlying cause. It risks disrupting legitimate neighbor relationships and can mask the true problem, leading to recurring issues. From a regulatory or ethical standpoint, this approach demonstrates a lack of due diligence and a failure to adhere to systematic troubleshooting methodologies expected in network operations. It could be seen as negligent if it leads to prolonged or repeated outages. Another incorrect approach is to focus solely on the physical layer connectivity without considering the routing protocol state. While physical issues can cause OSPF problems, assuming a physical fault without verifying the OSPF configuration and neighbor states is premature. This bypasses critical diagnostic steps within the routing protocol itself and could lead to misallocation of resources and time. Ethically, this represents a failure to apply the appropriate level of technical expertise and a deviation from standard operating procedures for routing protocol troubleshooting. A third incorrect approach is to modify OSPF timers without a clear understanding of their impact or a hypothesis about their role in the problem. OSPF timers are critical for network stability and convergence. Arbitrarily changing them can lead to flapping adjacencies, increased CPU utilization, or slow convergence, exacerbating the original issue or creating new ones. This demonstrates a lack of understanding of OSPF protocol mechanics and a disregard for the potential negative impacts, which is professionally unsound and could violate service-level agreements or operational guidelines. Professional reasoning. Professionals should adopt a structured troubleshooting methodology. This involves 1. Clearly defining the problem and its impact. 2. Gathering relevant information. Logs show commands topology. 3. Formulating a hypothesis. 4. Testing the hypothesis systematically. 5. Implementing a solution based on the confirmed hypothesis. 6. Verifying the solution and monitoring for recurrence. In this scenario, the professional decision-making process would prioritize examining OSPF neighbor states and the LSA database as the most direct path to understanding the routing protocol's behavior. This methodical approach ensures that solutions are targeted, effective, and minimize disruption, aligning with professional responsibility and operational best practices. Question 4. The efficiency study reveals that OSPF adjacencies on a specific network segment are taking an unusually long time to establish, impacting overall network convergence. Which of the following actions, if taken without further investigation into the root cause, would represent the least effective approach to resolving this issue while adhering to best practices for network stability and performance? Option A. Systematically reviewing and adjusting OSPF hello, dead, and wait for hello timers to align with network characteristics and convergence requirements. Option B. Changing the OSPF network type to broadcast on all interfaces within the segment, assuming this will simplify adjacency formation. Option C. Increasing the OSPF dead interval significantly to allow more time for neighbor discovery and reduce the likelihood of premature neighbor state drops. Option D. Disabling OSPF authentication on the affected interfaces to expedite the neighbor establishment process by removing verification overhead. The correct answer is A. Systematically reviewing and adjusting OSPF hello, dead, and wait for hello timers to align with network characteristics and convergence requirements. Explanation. The efficiency study reveals a recurring pattern of suboptimal convergence times for OSPF adjacencies across a critical segment of the Alcatel Lucent network. This scenario is professionally challenging because network engineers must balance the immediate need for network stability and performance with the long-term implications of routing protocol configuration. The pressure to restore full connectivity quickly can lead to hasty decisions that might violate best practices or even implicit regulatory expectations for network reliability and security, even if not explicitly codified in a specific document for this exam. The correct approach, which involves a systematic review of OSPF timers, hello, dead, and wait for hello, and their impact on adjacency establishment, represents best professional practice. This is because it directly addresses the root cause of slow convergence by adhering to the fundamental principles of OSPF design and operation. By ensuring timers are appropriately tuned for the network environment, engineers uphold the implicit regulatory expectation of maintaining a stable and responsive network infrastructure, which is crucial for business continuity and service delivery. This methodical approach minimizes the risk of introducing new issues and ensures a robust, predictable routing environment. An incorrect approach of simply increasing the dead interval without understanding the underlying cause is professionally unacceptable. This failure stems from a lack of deep analysis and a superficial fix. It violates the implicit regulatory expectation of maintaining an efficient and responsive network by masking, rather than resolving, the convergence issue. Furthermore, it can lead to longer undetected outages if a link does fail, as the network will take longer to detect and react to the failure. Another incorrect approach, such as indiscriminately disabling OSPF authentication, is a severe regulatory and ethical failure. While it might appear to speed up adjacency establishment by removing a verification step, it fundamentally compromises network security. This directly contravenes the implicit regulatory expectation of protecting network infrastructure from unauthorized access and manipulation, which could lead to service disruption or data breaches. It demonstrates a disregard for the integrity and trustworthiness of the routing information exchanged. A third incorrect approach, focusing solely on increasing the OSPF network type to broadcast without investigating the underlying link characteristics, is also professionally flawed. While broadcast networks can simplify adjacency formation in certain scenarios, forcing this change without understanding why adjacencies are slow to form on the current network type ignores potential underlying issues like packet loss or high latency on the physical links. This represents a failure to adhere to best practices in network design, which emphasizes understanding and optimizing for the specific environment rather than applying a generic, potentially detrimental solution. It also implicitly violates the expectation of maintaining an efficient network by not addressing the actual problem. The professional decision-making process for similar situations should involve a structured troubleshooting methodology. This includes 1. Clearly defining the problem and its impact. 2. Gathering relevant data, logs, interface statistics, OSPF neighbor states. 3. Forming hypotheses about the root cause. 4. Testing these hypotheses systematically. And 5. Implementing and verifying the solution. In this case, the hypothesis should center on OSPF timer misconfigurations or environmental factors affecting OSPF packet delivery, leading to a focused investigation of timer values and link health. Question 5. During the evaluation of a planned network maintenance window, it is observed that the OSPF-designated router (DR) election process on a critical segment is failing to complete, preventing the establishment of full adjacencies and impacting routing convergence. What is the most appropriate immediate course of action to address this OSPF-DR election failure? Option A. Reboot all routers participating in the OSPF domain to clear any potential transient states that might be preventing the DR election. Option B. Immediately force a DR election by manually configuring the DR and BDR roles on specific interfaces to restore adjacencies. Option C. Disable OSPF on the affected segment and revert to static routing for the duration of the maintenance window to ensure connectivity. Option D. Systematically investigate the OSPF neighbor states, interface configurations, and hello/dead timer settings on all routers participating in the OSPF segment to identify the root cause of the election failure. The correct answer is D. Systematically investigate the OSPF neighbor states, interface configurations, and hello/dead timer settings on all routers participating in the OSPF segment to identify the root cause of the election failure. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol feature, specifically OSPF-designated router (DR) election process, is not functioning as expected during a planned maintenance window. The challenge lies in balancing the urgency of restoring full network functionality with the need to avoid introducing further instability or unintended consequences. The pressure to resolve the issue quickly, coupled with the potential impact on network services, requires a systematic and informed approach to troubleshooting and resolution. The decision maker must consider the immediate impact of the DR election failure, potential workarounds, and the long-term implications of any chosen solution. Correct approach analysis. The correct approach involves a methodical investigation into the OSPF-DR election process, focusing on the underlying causes of the failure. This includes verifying OSPF neighbor adjacencies, checking interface states, and examining OSPF hello and dead timers. The goal is to identify the specific misconfiguration or network condition, preventing a successful DR election. Once the root cause is identified, a targeted solution can be implemented, such as correcting interface configurations, adjusting timers, or resolving network connectivity issues between potential DRs. This approach represents best professional practice because it adheres to established network troubleshooting methodologies, prioritizing a permanent fix over a temporary workaround. It minimizes the risk of introducing new problems by addressing the fundamental issue. From a regulatory and ethical standpoint, this methodical approach ensures network stability and reliability, which are paramount for maintaining service-level agreements and preventing service disruptions that could have financial or operational repercussions for the organization. Incorrect approaches analysis. One incorrect approach would be to immediately disable OSPF on the affected segment or force a DR election without understanding the cause. This is professionally unacceptable because it bypasses the diagnostic process and could mask underlying issues, leading to intermittent problems or complete network failure later. Ethically, it demonstrates a lack of due diligence and a disregard for network stability. Another incorrect approach would be to simply reboot all routers involved in the OSPF domain. While this might temporarily resolve the DR election issue, it is a brute force method that does not address the root cause. It risks disrupting other network services and is not a sustainable solution. This approach fails to meet professional standards by not performing proper root cause analysis and could be seen as negligent if it leads to further network degradation. A third incorrect approach would be to manually assign the DR/BDR roles to specific interfaces without understanding why the automatic election failed. This bypasses the dynamic nature of OSP and can lead to suboptimal routing or conflicts if the network topology changes. It is a reactive measure that does not contribute to a stable and resilient network design and could violate best practices for dynamic routing protocol operation. Professional reasoning. Professionals should employ a structured decision-making framework when faced with such network issues. This framework typically involves 1. Problem identification. Clearly define the observed behavior, e.g., no DR elected. 2. Information gathering. Collect relevant data including router logs, interface status, OSP neighbor states, and configuration details. 3. Hypothesis generation. Formulate potential causes for the observed problem. 4. Hypothesis testing. Systematically test each hypothesis through configuration checks, packet captures, or controlled experiments. 5. Solution implementation. Apply the identified fix. 6. Verification. Confirm that the issue is resolved and no new problems have been introduced. 7. Documentation. Record the problem, the solution, and lessons learned. This systematic approach ensures that decisions are data-driven, minimizes risk, and promotes long-term network health. Question 6. Strategic planning requires a robust approach to network stability and high availability. When faced with an unexpected routing instability impacting a critical service, what is the most professionally sound method for addressing the issue, ensuring both immediate resolution and long-term network integrity? Option A. Implement ad hoc configuration changes based on suggestions from colleagues who have encountered similar, but not identical, issues. Option B. Temporarily disable a high availability feature within the routing protocol to restore connectivity, with the intention of addressing its re-enablement later. Option C. Immediately revert to the last known stable configuration, assuming the current issue is a regression. Option D. Engage a senior network engineer to analyze logs and configuration, consult relevant documentation, and develop a targeted, tested solution before implementation. The correct answer is C. Immediately revert to the last known stable configuration, assuming the current issue is a regression. Explanation. This scenario presents a common challenge in network operations, balancing the immediate need for service restoration with the long-term implications of configuration changes. The professional challenge lies in making a rapid, informed decision under pressure, where a hasty choice could lead to further instability or security vulnerabilities, while a delayed decision could impact business continuity. The regulatory framework for Alcatel Lucent interior routing protocols and high availability, as interpreted within the context of typical telecommunications operational guidelines, emphasizes stability, predictability, and adherence to established change management processes, even during outages. The correct approach represents best professional practice because it prioritizes a systematic, documented, and validated method for resolving the routing issue. This aligns with industry best practices for network management, which mandate thorough analysis before implementing changes that affect critical infrastructure. Specifically, it adheres to the implicit regulatory expectation of maintaining network integrity and minimizing the risk of cascading failures. By involving a senior engineer and consulting documentation, the process ensures that the solution is not only effective, but also sustainable and auditable, reducing the likelihood of recurrence and ensuring compliance with any operational service level agreements, SLAs, or internal governance. An incorrect approach that involves immediately reverting to a previous known good configuration without understanding the root cause of the current instability is professionally unacceptable. This bypasses the diagnostic process and fails to address the underlying problem, potentially masking a more significant issue or reintroducing a previously resolved vulnerability. Ethically and regulatorily, this could be seen as a failure to exercise due diligence in network management, potentially violating implicit requirements for proactive problem-solving and risk mitigation. Another incorrect approach, such as making ad hoc configuration changes based on anecdotal evidence or peer suggestions without verification, is also professionally flawed. This introduces an unacceptable level of risk. It lacks the rigor required for critical network infrastructure, potentially leading to unintended consequences, further service disruption, or security breaches. Such actions would likely contravene operational guidelines that stress controlled and tested modifications to routing protocols. Finally, an approach that involves disabling a critical routing protocol feature to restore connectivity without a clear plan for its subsequent re-enablement and testing, is also problematic. While it might offer a quick fix, it compromises the intended high-availability design of the network. This could lead to a single point of failure if the feature is not properly restored, violating the core principles of high availability and potentially leading to non-compliance with service resilience requirements. The professional decision-making process for similar situations should involve a structured incident response methodology. This includes 1. Incident identification and assessment, quickly understanding the scope and impact of the issue. 2. Diagnosis, systematically gathering data and analyzing logs to pinpoint the root cause. 3. Solution development, proposing and evaluating potential solutions, considering their impact on stability, security, and availability. 4. Implementation, executing the chosen solution in a controlled manner with rollback plans in place. 5. Verification and documentation, confirming the resolution and thoroughly documenting the incident, cause, and solution for future reference and continuous improvement. Question 7. The control framework reveals an intermittent packet loss issue affecting a critical service. Network engineers are tasked with resolving this without impacting ongoing operations. Which of the following diagnostic and resolution strategies best adheres to professional best practices for maintaining high availability in an Alcatel Lucent interior routing environment? Option A. Randomly adjust BGP timer values and OSPF hello intervals on multiple routers in the affected area to observe if the packet loss subsides. Option B. Focus solely on physical layer diagnostics, such as checking cable integrity and transceiver status, without correlating these findings with routing protocol behavior or traffic patterns. Option C. Immediately initiate a rollback to the last known stable configuration across all affected network segments, assuming the recent changes are the cause. Option D. Systematically gather and analyze current routing table states, interface statistics, and relevant syslog messages from affected and adjacent network devices to identify anomalies, then formulate a targeted resolution based on this evidence. The correct answer is D. Systematically gather and analyze current routing table states, interface statistics, and relevant syslog messages from affected and adjacent network devices to identify anomalies, then formulate a targeted resolution based on this evidence. Explanation. The control framework reveals a common challenge in network operations, balancing the need for rapid troubleshooting with the imperative to maintain network stability and adhere to established operational procedures. In a high-availability routing environment, hasty configuration changes, even with good intentions, can inadvertently trigger cascading failures or disrupt critical services. The professional challenge lies in diagnosing the root cause of intermittent packet loss without introducing further instability. The correct approach represents best professional practice because it prioritizes a systematic, evidence-based methodology. By first gathering comprehensive diagnostic data, e.g., logs, interface statistics, routing table states, and analyzing it against known network behavior and established baselines, engineers can pinpoint the source of the issue. This methodical approach minimizes the risk of unintended consequences and ensures that any subsequent corrective actions are targeted and effective. It aligns with the principles of responsible network management, emphasizing stability and service continuity, which are paramount in high-availability scenarios. An incorrect approach that involves immediately reverting to a previous known good configuration without thorough analysis fails to address the underlying problem. This is professionally unacceptable because it masks the symptom rather than curing the disease. It could lead to the same issue recurring, potentially with greater impact. Ethically, it represents a failure to diligently investigate and resolve the problem, potentially impacting service-level agreements and customer trust. Another incorrect approach, such as randomly adjusting routing parameters on multiple routers simultaneously, is highly unprofessional and dangerous in a production environment. The shotgun approach significantly increases the probability of introducing new, more severe problems, potentially leading to a complete network outage. It demonstrates a lack of understanding of the interconnectedness of routing protocols and the potential for widespread disruption. This violates the fundamental responsibility to maintain network integrity. A further incorrect approach, focusing solely on the symptoms without examining the control plane or data plane interactions, is also professionally deficient. For instance, only looking at interface error counters without correlating them with routing adjacencies or traffic patterns would miss crucial diagnostic information. This superficial analysis can lead to misdiagnosis and ineffective solutions, wasting valuable time and resources, and potentially prolonging service degradation. The professional decision-making process for similar situations should involve a structured troubleshooting methodology. This typically includes 1. Defining the problem clearly, 2. Gathering all relevant data, 3. Forming a hypothesis, 4. Testing the hypothesis systematically, 5. Implementing a solution, and 6. Verifying the resolution. In high-availability environments, the emphasis is always on minimizing risk, prioritizing non-disruptive diagnostic techniques, and ensuring that any changes are well documented and have a clear rollback plan. Question 8. Regulatory review indicates that an Alcatel Lucent IS's implementation is experiencing intermittent adjacency flaps and LSP flooding issues. Network engineers suspect a protocol instability, but are unsure of the precise cause. Which of the following diagnostic and resolution approaches best aligns with maintaining service availability and network integrity? Option A. Immediately reset the IS's process on all routers exhibiting adjacency flaps to force a clean restart of the protocol and re-establish adjacencies. Option B. Initiate a comprehensive IS's protocol debug on all potentially affected routers. Meticulously analyze the generated logs for specific error messages or patterns related to neighbor state transitions and LSP processing, and correlate these findings with recent network configuration changes or hardware health checks before proposing any corrective actions. Option C. Focus troubleshooting efforts exclusively on analyzing traffic flow anomalies and packet loss metrics, assuming the IS's protocol itself is functioning correctly but is being impacted by external factors. Option D. Arbitrarily adjust IS's hello and dead timers on routers experiencing flaps, aiming to find a configuration that stabilizes the adjacencies. The correct answer is B. Initiate a comprehensive IS's protocol debug on all potentially affected routers. Meticulously analyze the generated logs for specific error messages or patterns related to neighbor state transitions and LSP processing, and correlate these findings with recent network configuration changes or hardware health checks before proposing any corrective actions. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol, IS's in this case, experiences intermittent instability. The professional challenge lies in diagnosing the root cause of this instability without causing further disruption to services, especially in a high-availability environment. The pressure to restore stability quickly must be balanced against the risk of making an incorrect change that could exacerbate the problem or lead to a complete outage. The intermittent nature of the issue adds complexity, as it may not be immediately reproducible. Correct approach analysis. The correct approach involves a systematic, data-driven investigation. This begins with comprehensive logging and monitoring of IS's adjacencies, LSP, and traffic flow. Analyzing these logs for patterns, such as specific neighbor flaps, LSP flooding issues, or unexpected route changes, is crucial. Correlating these events with any recent network changes or hardware diagnostics provides vital context. This methodical approach aligns with best practices for network troubleshooting, emphasizing evidence-based decision-making and minimizing reactive, potentially harmful, changes. It adheres to the implicit regulatory expectation of maintaining service availability and network integrity through diligent operational procedures. Incorrect approach is analysis. One incorrect approach is to immediately reset IS's on all affected routers. This is a blunt instrument that, while potentially resolving the immediate adjacency issue, fails to identify the underlying cause. It could mask a more serious problem, such as a hardware fault or a configuration error that will re-emerge. This reactive measure risks causing a wider disruption if the reset itself triggers unforeseen consequences, or if the original problem was not related to the IS's process itself. Another incorrect approach is to arbitrarily adjust IS's timers, e.g., hello, dead, LSP retransmission intervals, without a clear understanding of why the current timers are failing. While timer tuning can be a valid troubleshooting step, doing so without diagnostic data is speculative. It could lead to an unstable network state where adjacencies flap more frequently or LSPs are not generated or acknowledged correctly, further degrading routing stability. This approach lacks the rigor expected in maintaining critical network infrastructure. A third incorrect approach is to focus solely on traffic patterns and ignore IS's protocol-specific metrics. While traffic anomalies can be a symptom of routing issues, they are not the root cause in this context. Neglecting the IS's protocol's health and behavior means missing direct evidence of the problem. This could lead to misdiagnosis and the implementation of solutions that do not address the actual routing instability. Professional reasoning. Professionals should employ a structured troubleshooting methodology. This involves 1. Define the problem, clearly articulate the observed symptoms of IS's instability. 2. Gather information, collect all relevant logs monitoring data and network state information. 3. Analyze data, identify patterns, anomalies, and potential root causes based on the collected evidence. 4. Formulate hypotheses, develop educated guesses about the cause of the instability. 5. Test hypotheses, implement targeted tests or changes to validate or invalidate hypotheses, starting with non-disruptive methods. 6. Implement solution. Once the root cause is identified, implement the most appropriate and least disruptive fix. 7. Verify solution. Confirm that the problem is resolved and monitor for recurrence. This systematic process ensures that decisions are informed, risks are mitigated, and the network's stability and availability are prioritized. Question 9. Process analysis reveals that a critical Alcatel Lucent router, responsible for core interior routing protocol operations, is experiencing intermittent route processor failures. To ensure continuous network service availability and minimize user impact, what is the most effective and professionally sound approach to implement high availability for the routing functions? Option A. Rely solely on the inherent convergence time of the interior routing protocol to re-establish connectivity after a route processor failure. Option B. Utilize the platform's integrated stateful failover and redundant route processor capabilities to synchronize routing protocol states and enable rapid, automatic failover. Option C. Develop custom software scripts to monitor the routing process and trigger manual failover commands on a standby device. Option D. Implement a manual configuration backup and restore process to be executed by network engineers in the event of a route processor failure. The correct answer is B. Utilize the platform's integrated stateful failover and redundant route processor capabilities to synchronize routing protocol states and enable rapid, automatic failover. Explanation. Scenario analysis. This scenario presents a common challenge in network operations, ensuring high availability of critical routing services. The professional challenge lies in selecting the most appropriate mechanism to achieve redundancy and rapid failover for an Alcatel Lucent routing platform, specifically within the context of interior routing protocols. The need for a robust and efficient solution is paramount, as network downtime can lead to significant service disruptions and financial losses. The decision requires a deep understanding of the capabilities and limitations of different high-availability features offered by the platform, and how they interact with the chosen interior routing protocol, e.g., IS's or OSP. Correct approach analysis. The correct approach involves leveraging the platform's native high-availability features designed for routing protocol state synchronization and rapid failover. This typically includes mechanisms like redundant route processors and stateful failover capabilities. These features are engineered to maintain the routing state across redundant hardware components. In the event of a primary route processor failure, the secondary can take over with minimal disruption, often preserving the routing tables and neighbor adjacencies. This aligns with best professional practice by utilizing vendor-specific, integrated solutions that are optimized for performance and reliability, minimizing the risk of configuration errors, and ensuring compliance with the implicit requirement for service continuity inherent in network operations. Incorrect approach is analysis. Implementing a purely software-based, external heartbeat mechanism without leveraging the platform's integrated HA features is an incorrect approach. This would likely introduce significant latency and complexity, as it would require custom scripting or third-party tools to monitor routing process health and trigger failover. Such an approach is prone to race conditions, delays in detection, and potential inconsistencies in routing state synchronization, leading to prolonged network outages. Ethically, this represents a failure to utilize the most reliable and tested solutions available, potentially exposing the network to unacceptable risks. Relying solely on the inherent convergence time of the interior routing protocol itself to recover from a route processor failure is also an incorrect approach. While routing protocols are designed to reconverge, this process can take seconds to minutes, which is often unacceptable for critical services requiring near-instantaneous failover. This approach fails to meet the implicit service level agreements, SLAs, for high availability and demonstrates a lack of understanding of the platform's advanced HA capabilities. Manually intervening to reconfigure routing protocols on a standby device after a failure is a highly inefficient and error-prone method. This approach is reactive rather than proactive, introduces significant manual effort, and is susceptible to human error, which can exacerbate network issues. It completely bypasses the automated and integrated HA mechanisms designed to prevent such scenarios. Professional reasoning. Professionals should employ a decision-making framework that prioritizes understanding the specific requirements for availability and the capabilities of the deployed hardware and software. This involves 1. Requirement gathering. Clearly define the acceptable downtime and recovery time objectives, RTO, for the services relying on the routing platform. 2. Vendor documentation review. Thoroughly study the Alcatel Lucent documentation for the specific platform and software version to understand its native high availability features, including routing protocol state synchronization and failover mechanisms. 3. Feature selection. Choose the most appropriate integrated HA features that meet the defined RTOs and are designed for the specific routing protocols in use. 4. Testing and validation. Rigorously test the implemented HA solution through simulated failures to ensure it performs as expected and meets the availability requirements. 5. Continuous monitoring. Implement robust monitoring to detect potential issues with the HA configuration and the health of redundant components. Question 10. The control framework reveals that a critical data center network segment, relying on OSP for interior routing, is experiencing intermittent connectivity issues during planned maintenance events that involve router reloads. The network administrator needs to implement a solution to minimize service disruption and ensure rapid restoration of connectivity upon router recovery, without significantly increasing the complexity of the OSP configuration or introducing new single points of failure. Which of the following approaches best addresses this requirement for high availability within the OSP domain? Option A. Disable OSP on all routers and implement a static routing solution with manual route updates to manage traffic flow during maintenance. Option B. Configure OSP with aggressive timer values for hello and dead intervals to ensure quick detection of neighbor loss and rapid network reconvergence. Option C. Leverage OSP inherent fast convergence capabilities by enabling features such as OSP3 Fast Reroute FRR, or equivalent mechanisms for rapid traffic redirection around failed or restarting routers. Option D. Implement OSP with its default timer values and ensure that all critical services are manually restarted and verified after each router reload. The correct answer is B. Configure OSP with aggressive timer values for hello and dead intervals to ensure quick detection of neighbor loss and rapid network reconvergence. Explanation. The scenario presents a common challenge in network operations, ensuring high availability of critical routing services while managing the complexities of protocol convergence and potential failure points. Professional challenge lies in balancing the need for rapid failover with the risk of network instability caused by misconfigured or overly aggressive redundancy mechanisms. Careful judgment is required to select and implement solutions that meet stringent uptime requirements without introducing new vulnerabilities. The correct approach represents best professional practice because it prioritizes a robust and well-tested method for achieving high availability. By focusing on the inherent redundancy and fast convergence capabilities of OSP, and by implementing appropriate mechanisms like Fast Reroute FRR or equivalent, the network administrator is leveraging established and reliable techniques. This approach aligns with industry best practices for interior routing protocols, aiming to minimize downtime and maintain service continuity. The regulatory framework for telecommunications, while not explicitly detailed here due to the exam scope, implicitly mandates service reliability, and this method directly addresses that. An incorrect approach that relies solely on increasing timer values e.g., hello or dead timers, is professionally unacceptable. This is because while it might reduce the frequency of routing updates and potentially lessen the load on routers, it significantly increases convergence time. In a high availability context, slow convergence directly translates to extended service disruption, failing to meet the implicit regulatory and customer expectations for uptime. This approach demonstrates a fundamental misunderstanding of the trade-offs involved in routing protocol tuning for availability. Another incorrect approach that involves disabling all forms of redundancy and relying on manual intervention for failover is also professionally unacceptable. This directly contradicts the principles of high availability and would lead to prolonged and unpredictable service outages. Manual intervention is inherently slow and prone to human error, making it unsuitable for critical network infrastructure. This approach fails to meet even basic service-level agreements and would likely violate regulatory requirements for network resilience. A third incorrect approach that involves implementing a complex, proprietary, and untested failover mechanism without thorough validation is professionally risky and unacceptable. While innovation is valuable, introducing unproven solutions into a critical routing environment without rigorous testing can lead to unforeseen failures, instability, and extended downtime. This approach bypasses established best practices and could result in significant service degradation, potentially leading to regulatory scrutiny and loss of customer trust. A professional decision-making process for similar situations should involve a thorough understanding of the specific routing protocol's capabilities and limitations, a clear definition of availability requirements, and a risk assessment of potential solutions. Professionals should always favor well-documented, industry-standard, and thoroughly tested methods for achieving high availability. This includes understanding the impact of timer configuration, the benefits of advanced features like FRR, and the importance of rigorous testing before deploying any changes in a production environment. Question 11. Implementation of OSPF timer tuning in a large enterprise network to improve convergence time after link failures, considering the trade-offs between rapid detection and potential network instability. Option A. Maintain default OSPF hello and dead intervals to ensure maximum stability and avoid any potential for flapping. Option B. Significantly decrease OSPF hello and dead intervals to achieve near-instantaneous convergence. Option C. Slightly reduce OSPF hello and dead intervals to expedite neighbor failure detection and route recalculation. Option D. Increase OSPF hello and dead intervals to minimize LSA flooding and reduce router overhead. The correct answer is C. Slightly reduce OSPF hello and dead intervals to expedite neighbor failure detection and route recalculation. Explanation. The scenario presents a common challenge in network design, balancing the need for rapid convergence in routing protocols with the potential for instability and increased overhead. When implementing OSPF, a critical aspect is understanding how different timer values impact network behavior, particularly during topology changes. The professional challenge lies in selecting appropriate timer configurations that ensure timely route updates without overwhelming network devices or causing transient routing loops. This requires a deep understanding of OSPF internal mechanisms and the trade-offs involved. The correct approach involves a nuanced adjustment of OSPF timers, specifically the hello and dead intervals, to achieve a balance between fast convergence and stability. By slightly reducing these timers from their default values, network administrators can expedite the detection of neighbor failures and the subsequent propagation of routing updates. This proactive tuning, based on an understanding of the network's specific characteristics and traffic patterns, represents best professional practice. It demonstrates a commitment to optimizing network performance and resilience while adhering to the principles of efficient resource utilization, which are implicitly expected in professional network engineering. An incorrect approach would be to drastically reduce OSPF timers without thorough analysis. This could lead to excessive LSA flooding and neighbor adjacency flapping, causing network instability and performance degradation. Such an action would represent a failure to apply sound engineering principles and could violate implicit professional standards of care by introducing unnecessary risk. Another incorrect approach would be to ignore timer tuning altogether, relying solely on default values. While this might avoid immediate instability, it sacrifices the potential for faster convergence, which can be critical in high-availability environments. This passive approach fails to leverage the full capabilities of the routing protocol for optimal network operation. The professional decision-making process should involve a thorough assessment of the network's topology, size, and traffic patterns. Before making any timer adjustments, a detailed analysis of the potential impact on CPU utilization, memory usage, and LSA generation is essential. Simulation or testing in a lab environment is highly recommended to validate the chosen timer values. This iterative process of analysis, implementation, and validation ensures that network changes are made in a controlled and predictable manner, minimizing the risk of unintended consequences and maximizing the benefits of protocol tuning. Question 12. Operational review demonstrates a need to adjust OSPF network types and associated high-availability timers on a critical production router. What is the most prudent approach to ensure minimal service disruption and maintain network stability? Option A. Implement the proposed OSPF network type and timer changes directly on the production router during off-peak hours to minimize immediate user impact. Option B. Form a quick configuration review of the proposed changes and apply them to the production router, relying on the inherent resilience of OSPF to self-correct any issues. Option C. Conduct a comprehensive pre-change analysis, including simulation in a lab environment if possible, followed by a phased pilot deployment in a non-critical segment, and then a full deployment during a scheduled maintenance window with a tested rollback plan. Option D. Focus solely on the theoretical impact of the OSPF network type change on routing convergence, disregarding the specific high-availability timers and current network state. The correct answer is C. Conduct a comprehensive pre-change analysis, including simulation in a lab environment if possible, followed by a phased pilot deployment in a non-critical segment, and then a full deployment during a scheduled maintenance window with a tested rollback plan. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a network engineer to assess the impact of a proposed routing protocol change on network stability and performance without the benefit of a controlled lab environment or extensive historical data for the specific configuration. The pressure to implement changes quickly, coupled with the potential for widespread service disruption if the impact is underestimated, necessitates a rigorous and methodical approach to impact assessment. The inherent complexity of interior routing protocols and high availability mechanisms means that even seemingly minor changes can have cascading and unforeseen consequences. Correct approach analysis. The correct approach involves a phased deployment strategy, starting with a thorough pre-change analysis that includes reviewing existing network state, understanding the specific routing protocol behavior e.g. OSPF, ISs, and high availability features e.g. VRRP, BFD in the current environment, and simulating the proposed change in a controlled lab setting if possible. This is followed by a pilot deployment in a non-critical segment of the network, with extensive monitoring of key performance indicators, KPI, and routing stability metrics. Finally, a full deployment is executed during a scheduled maintenance window with rollback procedures clearly defined and tested. This approach represents best professional practice because it adheres to the principles of risk management and operational diligence. It minimizes the potential for service disruption by validating the change in a controlled manner before impacting the production environment. This aligns with general IT best practices for change management, which are implicitly supported by the need for reliable network services as expected by customers and stakeholders. While the 4A0-101 exam focuses on technical aspects, the underlying expectation is that these protocols are implemented and managed in a way that ensures service availability, a core tenet of professional network engineering. Incorrect approaches analysis. Implementing the change directly in the production environment without prior simulation or pilot testing is a significant regulatory and ethical failure. Demonstrates a disregard for service availability and customer impact, potentially violating service level agreements, SLAs, and leading to reputational damage. This approach is professionally unacceptable as it prioritizes speed over safety and stability. Performing a superficial review of the proposed configuration without understanding the specific interactions with existing routing adjacencies, link states, or high availability timers is another failure. This approach lacks the depth required for a complex routing environment and increases the risk of unexpected behavior. It shows a lack of due diligence and professional responsibility in ensuring the integrity of the network. Focusing solely on the theoretical behavior of the routing protocol in isolation, without considering the specific network topology, hardware capabilities, and existing high availability mechanisms, is also professionally unsound. Routing protocols do not operate in a vacuum. Their behavior is heavily influenced by the surrounding network elements. This narrow focus can lead to overlooking critical dependencies and potential failure points, thereby compromising network stability. Professional reasoning. Professionals should adopt a structured change management process that prioritizes risk assessment and mitigation. This involves understanding the what, why, and how of any proposed change, including its potential impact on all aspects of network operation. Before any production change, a thorough analysis should be conducted, including documentation review, simulation if feasible, and a pilot deployment. Clear rollback plans and comprehensive monitoring strategies are essential components of this process. The decision-making framework should always weigh the benefits of the change against the potential risks to service availability and performance, ensuring that the chosen path represents the most responsible and professional course of action. Question 13. The performance metrics show intermittent flapping of routes learned via OSP on several core routers, leading to packet loss and degraded application performance. The network engineer needs to identify the cause of this instability. Which of the following diagnostic approaches is most likely to lead to an accurate and efficient resolution? Option A. Immediately restart the OSP process on all core routers to clear any potential protocol state corruption. Option B. Focus solely on interface utilization and bandwidth usage on the affected links to identify congestion. Option C. Assume a physical layer issue and schedule immediate replacement of all network interface cards, NIC, on the routers experiencing route flapping. Option D. Examine OSP neighbor states, hello/dead timer configurations, and the link state advertisement, LSA, database for inconsistencies or rapid changes. The correct answer is D. Examine OSP neighbor states, hello/dead timer configurations, and the link state advertisement, LSA, database for inconsistencies or rapid changes. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a routing protocol, specifically OSP in this case, is exhibiting unexpected behavior impacting network stability. The professional challenge lies in accurately diagnosing the root cause of the flapping routes without disrupting ongoing services, while adhering to operational best practices and potentially regulatory compliance requirements related to network uptime and performance. The pressure to restore stability quickly must be balanced with the need for thorough, evidence-based troubleshooting. Correct approach analysis. The correct approach involves systematically analyzing the OSP neighbor adjacencies and the associated LSA, link state advertisement, database. This method is best professional practice because it directly addresses the core mechanisms of OSP operation. By examining neighbor states, timers, and LSA types, a network engineer can pinpoint whether the flapping is due to physical layer issues, misconfigurations in OSP parameters, like hello/dead timers, or problems with LSA flooding and aging. This systematic, protocol-centric investigation aligns with industry standards for network troubleshooting and ensures that the solution targets the actual cause, minimizing the risk of introducing further instability. While the exam syllabus for 4A0-101 focuses on Alcatel Lucent interior routing protocols, the underlying principles of OSP troubleshooting are universal and form the basis of professional network engineering. Incorrect approach is analysis. One incorrect approach would be to immediately reset all OSP interfaces or restart the OSP process on all affected routers. This is a brute force method that, while potentially resolving the issue, lacks diagnostic rigor. It fails to identify the root cause, making it difficult to prevent recurrence. From a professional standpoint, this approach is risky as it can lead to a complete network outage or prolonged downtime, violating implicit or explicit service level agreements, SLAs, and potentially regulatory requirements for network availability. Another incorrect approach would be to solely focus on interface utilization or bandwidth saturation without correlating it to OSP state changes. While high utilization can contribute to packet loss and thus OSP instability, it's not the direct cause of flapping routes in isolation. This approach misses the specific OSP protocol events that trigger route changes. Ethically and professionally, this is a failure to perform due diligence in diagnosing the problem, potentially leading to misallocation of resources and prolonged resolution times. A third incorrect approach might be to assume a hardware failure on the affected links and immediately schedule hardware replacement, without verifying OSP state and LSA integrity. This is premature and bypasses essential diagnostic steps. It can lead to unnecessary hardware costs and downtime if the issue is purely configuration related. Professionally, this demonstrates a lack of systematic troubleshooting and an over-reliance on assumptions rather than data. Professional reasoning. Professionals should approach such scenarios by first gathering all available data, including performance metrics, logs, and OSPF neighbor states. The next step is to form a hypothesis based on this data, and then systematically test it by examining the relevant OSPF protocol elements. This iterative process of data collection, hypothesis testing, and validation ensures that the most efficient and effective solution is implemented, minimizing service impact and adhering to professional standards of care in network management. Question 14. Investigation of the most effective strategy for implementing a critical routing configuration update on a live Alcatel Lucent network segment to enhance stability, while adhering to best practices for minimizing service disruption and ensuring regulatory compliance. Option A. Implement the configuration changes directly on the live production network segment, assuming the changes are minor and unlikely to cause significant disruption. Option B. Immediately roll back all configuration changes as soon as any minor anomaly is detected in the network, without further investigation. Option C. Conduct thorough pre-deployment testing in a lab environment that accurately simulates the production network, followed by a phased rollout in the production environment, starting with a non-critical segment and closely monitoring for any adverse effects. Option D. Focus exclusively on the immediate symptoms of the routing issue and apply a quick fix without considering the broader network context or the potential impact of the configuration change. Correct answer is C. Conduct thorough pre-deployment testing in a lab environment that accurately simulates the production network, followed by a phased rollout in the production environment, starting with a non-critical segment and closely monitoring for any adverse effects. Explanation. Scenario analysis. This scenario presents a professional challenge related to network stability and service continuity, directly impacting the reliability of critical network infrastructure. The challenge lies in balancing the need for proactive network maintenance and upgrades with the imperative to avoid service disruption. Network engineers must possess a deep understanding of routing protocol behavior, failover mechanisms, and the potential ripple effects of configuration changes on a live network. The pressure to resolve issues quickly, coupled with the inherent complexity of routing protocols, necessitates a methodical and well-informed approach to troubleshooting and configuration management. Correct approach analysis. The correct approach emphasizes a systematic, phased, and controlled deployment of configuration changes. This involves thorough pre-deployment testing in a lab environment that accurately mirrors the production network's topology and configuration. Following this, a staged rollout in the production environment, starting with a non-critical segment and closely monitoring for adverse effects, is crucial. This methodology aligns with best practices for network change management, aiming to minimize risk and ensure service availability. The regulatory framework for network operations, while not explicitly detailed in the exam syllabus, implicitly mandates adherence to principles of due diligence and risk mitigation to prevent service degradation or outages that could impact end users or business operations. This approach demonstrates professional responsibility and a commitment to maintaining network integrity. Incorrect approaches analysis. Implementing configuration changes directly on the live production network without prior testing is a significant regulatory and ethical failure. It demonstrates a disregard for the potential impact on service availability and violates the principle of due diligence. Such an action could lead to widespread network instability, service outages, and potential financial or reputational damage to the organization, which could have regulatory implications if service-level agreements are breached. Rolling back all changes immediately upon encountering any minor anomaly without proper investigation is also professionally unsound. While caution is necessary, an immediate rollback without understanding the root cause can mask underlying issues, prevent necessary improvements. This approach lacks the analytical rigor required for effective network management and can lead to recurring problems. It fails to demonstrate a proactive and problem-solving mindset, focusing solely on the immediate symptoms of a routing issue without considering the broader network context or the impact of the proposed configuration change is another failure. This narrow focus can lead to temporary fixes that do not address the fundamental problem, potentially exacerbating it or causing new issues elsewhere in the network. It demonstrates a lack of holistic network understanding and a failure to apply comprehensive troubleshooting methodologies. Professional reasoning. Professionals should adopt a structured change management process that includes detailed planning, risk assessment, lab testing, phased deployment, and continuous monitoring. When troubleshooting, a systematic approach involving data collection, hypothesis generation, testing, and validation is essential. Understanding the interdependencies within the routing environment and the potential impact of any change on overall network stability is paramount. This methodical approach ensures that network operations are conducted responsibly, minimizing risks and maintaining service continuity, thereby adhering to implicit regulatory expectations of reliable service delivery. Question 15. What factors determine the most appropriate interior routing protocol selection for an Alcatel Lucent network environment, considering the need for high availability and efficient traffic management, without solely relying on administrative distance as the primary metric? Option A. The protocol's convergence speed, scalability to handle network growth, and its inherent security features. Option B. The protocol that is most widely adopted in the industry, irrespective of specific network topology. Option C. The protocol with the lowest administrative distance, regardless of other operational characteristics. Option D. The protocol that requires the least amount of configuration effort for initial deployment. Correct answer is A. The protocol's convergence speed, scalability to handle network growth, and its inherent security features. Explanation. This scenario presents a professional challenge because network engineers must balance the immediate need for network stability with the long-term implications of routing protocol design choices. The decision impacts not only current traffic flow, but also future scalability, security, and operational efficiency. Careful judgment is required to select a routing protocol that aligns with the organization's strategic goals and adheres to industry best practices, particularly within the context of Alcatel Lucent interior routing protocols. The correct approach represents best professional practice because it prioritizes a thorough understanding of the network's specific requirements, including traffic patterns, topology complexity, and convergence needs. Before selecting a routing protocol, this aligns with the principles of sound network engineering, which emphasize designing for resilience and efficiency. By considering factors like administrative distance, convergence speed, and scalability, engineers ensure the chosen protocol can effectively manage routing information, adapt to network changes, and maintain high availability. This proactive approach minimizes the risk of future performance issues or security vulnerabilities, thereby upholding professional responsibility. An incorrect approach that focuses solely on the lowest administrative distance without considering other critical factors is professionally unacceptable. This failure stems from a lack of comprehensive analysis and can lead to suboptimal routing decisions, increased convergence times, and potential instability. It neglects the fundamental requirement of selecting a protocol that best fits the network's operational demands. Another incorrect approach that prioritizes a protocol known for its simplicity over its ability to handle complex topologies or large routing tables is also professionally flawed. While simplicity can be appealing, it often comes at the cost of scalability and robustness, which are essential for maintaining high availability in modern networks. This choice demonstrates a failure to anticipate future network growth and potential challenges. A third incorrect approach that overlooks the security implications of a routing protocol, such as its susceptibility to route injection or manipulation, is a significant regulatory and ethical failure. Network security is paramount, and choosing a protocol without adequate security features or proper configuration can expose the network to serious threats, leading to data breaches and service disruptions. This violates the professional duty to protect network integrity and user data. The professional decision-making process for similar situations should involve a structured evaluation of routing protocol options against a defined set of criteria. This includes 1. Understanding network requirements. Analyze current and projected traffic volumes, network topology, and the need for rapid convergence. 2. Protocol feature comparison. Evaluate each protocol's administrative distance, convergence characteristics, scalability, and resource utilization. 3. Security assessment. Determine the protocol's inherent security features and the feasibility of implementing additional security measures. 4. Operational considerations. Assess the ease of configuration, monitoring, and troubleshooting for each protocol. 5. Organizational strategy alignment. Ensure the chosen protocol supports the organization's long-term network growth and business objectives. By following this systematic approach, network engineers can make informed decisions that ensure optimal network performance, security, and high availability. Question 16. When evaluating the implementation of OSP or ISs for high availability in a critical network segment, which approach best ensures adherence to operational best practices and minimizes the risk of service disruption, considering the need for rapid convergence and stable routing adjacencies? Option A. Prioritizing the fastest possible OSP/ISs convergence by aggressively tuning timers, without extensive pre-deployment testing of stability under adverse conditions. Option B. Implementing a comprehensive testing methodology that simulates various failure scenarios to validate OSP/ISs convergence times and failover mechanisms, documenting all results before production deployment. Option C. Deploying OSP/ISs configurations based on general vendor recommendations, without specific validation, against the network's unique topology and traffic patterns. Option D. Relying solely on the default OSP/ISs timer values provided by the vendor, assuming they are optimized for all network environments. The correct answer is B. Implementing a comprehensive testing methodology that simulates various failure scenarios to validate OSP/ISs convergence times and failover mechanisms, documenting all results before production deployment. Explanation. This scenario presents a professional challenge in network design and implementation by requiring adherence to specific Alcatel Lucent interior routing protocols and high availability guidelines within a regulated environment. The core difficulty lies in balancing the technical requirements for robust routing with the imperative to comply with established operational procedures and potential service level agreements, SLAs, that might be influenced by regulatory frameworks, even if not explicitly stated as a direct law in the question's context. The exam's focus on 4A0-101 implies a need to understand how these protocols are deployed in a manner that ensures network stability and resilience, which are often implicit requirements in telecommunications or enterprise network operations, governed by industry best practices and potentially contractual obligations. The correct approach represents best professional practice because it prioritizes a systematic and documented validation process that aligns with the principles of network engineering and operational excellence. This involves thorough testing of routing protocol convergence times and failover mechanisms under various simulated failure conditions. Such an approach ensures that the network's high availability objectives are met, minimizing potential service disruption. This aligns with the implicit regulatory expectation of reliable service delivery, which is a cornerstone of telecommunications and critical infrastructure operations. The process of documenting these tests and their outcomes provides an auditable trail, essential for demonstrating due diligence and compliance with internal policies and external expectations. An incorrect approach that focuses solely on achieving rapid convergence without considering the stability and predictability of the routing environment would be professionally unacceptable. This could lead to intermittent routing loops or black holes, directly contravening the goal of high availability and potentially violating service commitments. Another incorrect approach, which involves deploying configurations without rigorous pre-production testing, introduces significant risk of network instability and service outages. This demonstrates a failure to adhere to standard network engineering best practices and a disregard for the potential impact on end users or dependent services, which could have regulatory implications if service disruption thresholds are breached. A third incorrect approach, relying on vendor default configurations without customization or validation, ignores the specific network topology and traffic patterns, leading to suboptimal performance and potential instability, thus failing to meet the high availability requirements. The professional decision-making process for similar situations should involve a phased approach. First, understanding the specific requirements for routing protocol behavior and high availability as defined by the network's purpose and any contractual obligations. Second, designing the routing configuration to meet these requirements, considering factors like protocol choice, timers, and redundancy mechanisms. Third, conducting comprehensive testing in a lab environment that simulates realistic failure scenarios. Fourth, documenting all test results and configurations. Finally, implementing the validated configuration in a controlled manner, with rollback plans in place and continuous monitoring post-deployment. This structured methodology ensures that technical objectives are met while adhering to the implicit and explicit demands for network reliability and operational integrity. Question 17. Compliance review shows that an Alcatel Lucent router running OSP is exhibiting intermittent neighbor adjacency flaps, leading to unstable routing paths. Network engineers have observed that these flaps occur randomly throughout the day, impacting application performance. The review requires an assessment of the immediate troubleshooting steps taken by the operations team. Which of the following approaches represents the most effective and compliant method for diagnosing and resolving the OSP adjacency flaps? Option A. Increase the OSP hello and dead timers on all interfaces participating in the affected OSP area to reduce the frequency of hellos and potential adjacency resets. Option B. Immediately initiate a full OSP database synchronization across all routers in the area to refresh the link state database. Option C. Systematically verify the OSP configuration on the affected router, examine OSP neighbor states and timers, and analyze OSP interface status and error counters. Option D. Replace the network interface card, NIC, on the router experiencing the adjacency flaps, as this is a common cause of intermittent connectivity issues. The correct answer is B. Immediately initiate a full OSP database synchronization across all routers in the area to refresh the link state database. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol, OSP, is experiencing intermittent instability. The professional challenge lies in diagnosing the root cause of this instability without causing further disruption to the network. The pressure to restore full stability quickly, coupled with the potential impact on services, necessitates a methodical and informed approach. The complexity arises from the distributed nature of OSP and the potential for misconfigurations or environmental factors to manifest as routing anomalies. Careful judgment is required to balance the urgency of resolution with the need for thorough investigation and adherence to operational best practices. Correct approach analysis. The correct approach involves a systematic investigation that begins with verifying the OSP configuration on the affected routers. This includes checking key parameters such as network statements, area ID, authentication settings, and interface states. Following this, a detailed analysis of OSP neighbor adjacencies is crucial. Examining the OSP state transitions, hello/dead timers, and potential network segment issues, e.g., duplex mismatches, excessive packet loss, provides insight into why adjacencies might be flapping. The use of OSP-specific diagnostic commands to inspect the link state database, LSDB, for inconsistencies or unexpected changes is also paramount. This methodical, layered approach, starting with configuration and progressing to operational state and database integrity, aligns with industry best practices for network troubleshooting and ensures that the resolution is based on factual evidence rather than assumptions. This systematic process minimizes the risk of introducing new problems and maximizes the likelihood of identifying the true root cause. Incorrect approaches analysis. One incorrect approach is to immediately assume a hardware failure and initiate hardware replacement without sufficient diagnostic evidence. This is professionally unacceptable because it bypasses the fundamental troubleshooting steps for a routing protocol, can lead to unnecessary expenditure, downtime for hardware replacement, and may not resolve the underlying issue if the problem is configuration-related or a transient network condition. Another incorrect approach is to arbitrarily change OSP timers or parameters in an attempt to stabilize the network without understanding the impact of such changes. This is a failure of professional reasoning as it constitutes a shotgun approach to troubleshooting, which is inherently risky. Modifying critical OSP timers without a clear hypothesis or understanding of their function can lead to further instability, routing loops, or network black holes, violating the principle of least disruption. A third incorrect approach is to solely rely on network monitoring tools without performing on-device diagnostics. While monitoring tools are valuable for alerting and trend analysis, they often lack the granular detail required to pinpoint the root cause of protocol-specific issues. Failing to log into the affected devices and examine the protocol's operational state and logs represents a significant gap in due diligence and a failure to apply comprehensive diagnostic techniques. Professional reasoning. Professionals should approach such situations by first establishing a clear understanding of the problem's scope and impact. This involves gathering information from monitoring systems and affected users. The next step is to formulate a hypothesis based on the observed symptoms. Troubleshooting should then proceed in a logical, top-down or bottom-up manner, starting with the most likely causes and progressing to less probable ones. This involves verifying configurations, examining protocol states, analyzing logs, and using diagnostic tools. Throughout the process, it is crucial to document all actions taken and their observed effects. If a change is made, it should be done with a clear rollback plan. The ultimate goal is to identify the root cause and implement a permanent solution that prevents recurrence, while minimizing service disruption. Question 18. The performance metrics show intermittent packet loss and increased latency on several critical network segments. While link utilization on these segments is not consistently at its maximum, the issue correlates with periods of increased routing protocol churn and occasional disruptions in high-availability failover events. What is the most appropriate initial approach to diagnose the root cause of these performance degradations? Option A. Focus on increasing the bandwidth of the affected network links, assuming that the current capacity is insufficient to handle peak traffic demands, even if utilization metrics do not consistently show saturation. Option B. Analyze the state of interior routing protocol adjacencies and examine logs for routing flaps or convergence delays, while also reviewing the status and logs of high-availability protocols for any anomalies during the affected periods. Option C. Investigate external network factors, such as upstream provider congestion or denial-of-service attacks, as the primary cause, given the intermittent nature of the performance issues. Option D. Immediately initiate a hardware diagnostic sweep on all network devices connected to the affected segments to rule out physical layer issues. Correct answer is B. Analyze the state of interior routing protocol adjacencies and examine logs for routing flaps or convergence delays, while also reviewing the status and logs of high-availability protocols for any anomalies during the affected periods. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where performance degradation is observed, but the root cause is not immediately apparent. The professional challenge lies in accurately identifying the source of the issue within a complex routing environment, specifically concerning the Alcatel Lucent interior routing protocols and high-availability mechanisms. Misdiagnosing the problem can lead to incorrect remediation efforts, prolonged service disruption, and potential breaches of service-level agreements, SLAs, which are often governed by contractual obligations and industry best practices, implicitly requiring adherence to the principles of reliable network operation as outlined by vendors like Alcatel Lucent and general networking standards. The pressure to restore service quickly, coupled with the need for precise technical analysis, demands a systematic and informed approach. Correct approach analysis. The correct approach involves a methodical investigation that prioritizes understanding the impact of routing protocol behavior on network stability and availability. This means examining the specific routing protocol states, neighbor relationships, and route advertisements within the Alcatel-Lucent environment. For instance, analyzing OSPF or IS's neighbor adjacency states, BGP route flap damping, or the behavior of high-availability protocols like VRRP or GLBP during periods of instability is crucial. This approach aligns with best professional practice by directly addressing the core components of interior routing and high availability, ensuring that the investigation is focused and technically sound. It reflects a deep understanding of how these protocols function and interact, enabling the identification of subtle issues that might otherwise be overlooked. This methodical examination is implicitly required by the need to maintain network integrity and meet performance expectations, which are foundational to professional network engineering. Incorrect approaches analysis. Focusing solely on link utilization without considering the underlying routing dynamics is an incomplete approach. While high utilization can be a symptom, it doesn't explain why traffic is being routed inefficiently or why failover mechanisms might not be engaging correctly. This could lead to misdirected troubleshooting efforts, such as attempting to upgrade link capacity when the actual problem lies in suboptimal route selection or a failure in the high availability protocol state machine. This approach fails to acknowledge the intricate interplay between routing protocols and network performance, potentially violating the implicit requirement for thorough root cause analysis. Attributing the issue solely to external factors without investigating the internal routing configuration is also professionally unsound. While external events can impact a network, a robust interior routing and high availability design should be resilient to a degree. Ignoring the possibility of misconfigurations, protocol flapping, or failures within the Alcatel Lucent devices themselves means neglecting the primary area of responsibility for network engineers. This can lead to a failure to identify and rectify internal network vulnerabilities, potentially resulting in recurring or cascading failures. Blaming the hardware without a systematic diagnostic process is premature and unprofessional. Hardware failures can occur, but they are often the result of underlying software or configuration issues, or they manifest in specific, diagnosable ways. A proper investigation would involve checking hardware logs, performing diagnostic tests, and correlating any hardware alerts with observed routing or availability anomalies. Jumping to a hardware conclusion without this due diligence can lead to unnecessary hardware replacements and a failure to address the true root cause, which might be a software bug or a configuration error within the routing protocols. Professional reasoning. Professionals should adopt a structured troubleshooting methodology. This begins with clearly defining the observed symptoms and their impact. Next, they should form hypotheses about potential causes, prioritizing those directly related to the technologies in scope, Alcatel Lucent interior routing protocols, and high availability. Data collection should then focus on gathering evidence to support or refute these hypotheses, utilizing vendor-specific diagnostic tools and logs. The process involves iterative refinement of hypotheses as new data emerges. When dealing with routing and high availability, a deep dive into protocol states, neighbor adjacencies, route tables, and failover mechanism logs is paramount. This systematic approach ensures that resources are used efficiently, the true root cause is identified, and effective solutions are implemented, thereby upholding professional standards and contractual obligations. Question 19. The assessment process reveals that a network administrator is considering a change to the OSPF network type configuration on a critical router within an Alcatel Lucent network. The proposed change aims to optimize routing efficiency, but carries a risk of increased convergence time under certain failure scenarios. The administrator must decide on the best course of action to ensure network stability and performance. Which of the following approaches best aligns with professional best practices for managing such a change? Option A. Apply the OSPF network type change to a non-critical router first to observe its behavior, then proceed with the production router if no immediate issues are apparent. Option B. Conduct a comprehensive test of the proposed OSPF network type configuration in a lab environment that accurately simulates the production network's topology and traffic patterns before implementing it on the production router. Option C. Revert to a previously known stable, but less efficient, OSPF network type configuration without investigating the root cause of the current potential instability. Option D. Implement the OSPF network type change directly on the production router, relying on the router's inherent resilience to handle any unforeseen issues. The correct answer is D. Implement the OSPF network type change directly on the production router, relying on the router's inherent resilience to handle any unforeseen issues. Explanation. The assessment process reveals a common challenge in network operations, balancing the immediate need for network stability with the long-term benefits of protocol optimization. In this scenario, the network administrator is faced with a decision that directly impacts the reliability and efficiency of traffic flow within an Alcatel Lucent environment, specifically concerning the behavior of OSPF. The professional challenge lies in interpreting the implications of a specific OSPF configuration change on network convergence times and potential routing loops, especially in a production environment where downtime is unacceptable. Careful judgment is required to select the configuration that adheres to best practices for routing protocol stability and performance without introducing undue risk. The correct approach represents best professional practice because it prioritizes a controlled and validated implementation of changes. By first testing the proposed OSPF configuration in a lab environment that accurately mirrors the production network's topology and traffic patterns, the administrator can identify potential issues such as suboptimal metric calculations or unexpected adjacency formations before they impact live users. This proactive testing aligns with the fundamental principles of network engineering, which emphasize risk mitigation and thorough validation. Furthermore, documenting the testing methodology and results provides a clear audit trail and justification for the chosen configuration, essential for compliance and future troubleshooting. This methodical approach minimizes the likelihood of introducing routing instability or performance degradation, thereby upholding the service-level agreements and operational integrity of the network. An incorrect approach that involves immediately applying the OSPF configuration change to the production network without prior testing represents a significant regulatory and ethical failure. This reckless action disregards the potential for widespread service disruption, which could lead to financial losses for the organization and reputational damage. It violates the implicit ethical obligation of a network professional to maintain network stability and availability. Another incorrect approach, which is to revert to a previous, less optimal OSPF configuration without understanding the root cause of the current instability, is also professionally unacceptable. While it might temporarily restore service, it fails to address the underlying issue and misses an opportunity for network improvement. This approach demonstrates a lack of proactive problem solving and can lead to recurring issues, indicating a failure to meet professional standards of competence and diligence. The professional decision-making process for similar situations should involve a structured approach to change management. This includes 1. Thorough understanding of the proposed change and its potential impact. 2. Rigorous testing in a representative lab environment. 3. Development of a detailed implementation plan, including rollback procedures. 4. Communication with stakeholders regarding the plan change and potential risks. And 5. Post-implementation monitoring and verification. This framework ensures that changes are implemented safely, effectively, and with minimal disruption, upholding professional responsibility and adherence to operational best practices. Question 20. Benchmark analysis indicates that an Alcatel Lucent service provider network is experiencing intermittent OSPF route flapping. Network engineers need to address this instability. Which of the following diagnostic and resolution approaches represents the most professional and effective method for identifying and rectifying the root cause of the OSPF instability? Option A. Begin by examining OSPF neighbor adjacency states and analyzing the flooding of link state advertisements, LSA, to identify any anomalies or excessive updates. If no immediate cause is found, proceed to review OSPF timer configurations and interface states for potential misconfigurations or suboptimal settings. Option B. Randomly disable OSPF interfaces on various routers within the network to isolate the segment causing the route flapping. Option C. Immediately initiate a restart of the OSPF routing process on all routers within the affected routing area to clear any potential transient issues. Option D. Focus solely on increasing the OSPF dead interval timer across the entire network to reduce the frequency of neighbor adjacency resets. The correct answer is A. Begin by examining OSPF neighbor adjacency states and analyzing the flooding of link state advertisements, LSA, to identify any anomalies or excessive updates. If no immediate cause is found, proceed to review OSPF timer configurations and interface states for potential misconfigurations or suboptimal settings. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical routing protocol, OSPF, is experiencing intermittent instability. The professional challenge lies in diagnosing the root cause of this instability without causing further disruption to the production network. The pressure to restore stability quickly, coupled with the potential impact on services, necessitates a methodical and well-justified approach. The absence of a clear, immediate cause requires careful evaluation of multiple potential factors, each with its own implications for network performance and compliance. Correct approach analysis. The correct approach involves a systematic, layered investigation that prioritizes non-disruptive troubleshooting and leverages the inherent diagnostic capabilities of OSPF. This aligns with best professional practices for network management, which emphasize minimizing service impact and adhering to established operational procedures. By first examining OSPF neighbor adjacencies and LSA flooding, a network engineer can quickly identify common causes of instability without altering the network configuration. If these initial steps do not yield a resolution, a controlled examination of OSPF timers and interface states provides further diagnostic depth. This methodical progression ensures that changes are made only when necessary and are well understood, reducing the risk of introducing new problems. This approach is also implicitly supported by general IT best practices that advocate for a structured problem-solving methodology, often codified in ITIL or similar frameworks, which are standard in professional network operations. Incorrect approaches analysis, an approach that immediately focuses on modifying OSPF timers without a thorough understanding of the current state of neighbor adjacencies or LSA flooding, is professionally unsound. This is because it bypasses fundamental diagnostic steps and introduces configuration changes that could exacerbate instability or lead to routing loops, directly impacting service availability. Such an action would be considered a failure to follow a structured troubleshooting methodology, a core ethical expectation for network professionals. Another incorrect approach would be to immediately restart OSPF processes on all routers. This is a blunt instrument that, while sometimes effective, is highly disruptive and lacks precision. It fails to isolate the problem and could mask the underlying cause, making future troubleshooting more difficult. This action demonstrates a lack of due diligence and a disregard for service continuity, which are critical professional responsibilities. Finally, an approach that involves randomly disabling OSPF interfaces without a clear hypothesis or a plan to re-enable them is a significant professional and ethical failure. This is a highly disruptive action that would likely lead to widespread network outages and is not based on any logical diagnostic process. It represents a failure to apply sound engineering principles and a disregard for the impact on users and business operations. Professional reasoning. Professionals facing such a situation should employ a structured troubleshooting framework. This typically involves 1. Define the problem, clearly understand the symptoms and impact. 2. Gather information, collect relevant logs, status outputs, and network topology data. 3. Identify potential causes. Brainstorm a list of plausible reasons for the observed behavior. 4. Test hypotheses. Systematically test each potential cause, prioritizing non-disruptive methods. 5. Implement solutions. Apply changes based on confirmed causes with rollback plans. 6. Verify the solution. Confirm that the problem is resolved and no new issues have arisen. 7. Document the process, record findings, action, and resolutions for future reference. This systematic approach ensures that troubleshooting is efficient, effective, and minimizes risk to the production environment.